So let's talk about energy when we have something rotating. And here I have a hoop and a solid sphere, and I'm going to start them both from rest at the top of this inclined plane. Inclined plane is 15 meters long and at an angle of 25 degrees. So the first question I can ask myself is which one is going to get there first? What about their velocities? Which one's going to have a higher velocity? And which one is going to have the most energy at the bottom? So first, let's go ahead and lay out some of the fundamentals that we need. Before I can do anything with energy, I know that I'm going to have, let's see, potential energy up top when they're sitting still getting ready to roll. And at the bottom, let's see, I'm going to have just kinetic energy. That's an E. So the thing with kinetic energy when something is rolling is I have two pieces. So my KE total is going to equal, let's see, my translational kinetic energy, so my 1/2 mv squared, plus my rotational energy. So 1/2, instead of mass, now I have my moment of inertia, which is covered in a different video, and then multiplied by omega squared. So velocity is replaced with its rotational speed. All right, and now I need, if I'm going to relate potential energy to motion, then I definitely need the height of this thing. So I can remind myself, let's see, height is over here. So sine is opposite over hypotenuse. So sine of 25 is going to equal opposite over hypotenuse, h over 15. Or my height then is going to be 15 times sine of 25. Now be real careful here because we've been bouncing back between radians and degrees. This is given in degrees, so you want to double check on your calculators when you're doing problems like these. All right, so first thing is, what are you predicting? Who's going to get down first? Do you think the solid sphere will, or do you think the hoop will? Without doing any math, what's your intuition tell you? So let's check it out. So for my sphere, I'm going to have my potential energy, so mgh is going to go into 1/2 mass of the sphere, v squared, plus 1/2 I omega squared. So if I was asked to do anything math related with this, the one thing that would jump out at me is, while I can solve for this height, so I can solve for this piece, I don't know velocity and I don't know omega. My moment of inertia, well, I have that for the solid sphere, it's 2/5 mr squared, so that can be solved. But what about omega and velocity? So here I can remind myself that omega is the velocity divided by the radius. If you can't remember that, remember that omega is the same anywhere on a circle or a sphere, anything circular, right? The whole thing is rotating at the same rate. But if you think in terms of your bicycle wheel, the velocity is dependent on where it is on the radius of that circular thing. So if I am farther out, am I going faster or slower than when I'm closer into the center of something? So if omega is the same, the larger the r, the further out I am on something, the higher the velocity. So here we're just going to make that translation to saying, okay, I can make this substitution here into this equation, and so that gives me mgh equals 1/2 mv squared plus 1/2 I omega squared, so v squared over r squared. Cool. Now what about I? Let's do the last step and get rid of I. I is 2/5 mr squared, so mgh equals 1/2 mv squared plus 1/2 times 2/5 times mass times r squared times v squared over r squared. Okay, here. My radius cancels out. And now if I look, I have mass in every term, so it's going to cancel out. So gravity times height is going to give me 1/2 v squared plus the 2 is going to cancel out 1/5 v squared. So see, it's otherwise known as GH equals 7/10 v squared. And that's for the sphere. Cool. So if I want to solve for this as far as how fast or who gets down the hill who gets down the hill the first, then I want to isolate for velocity, because the higher the velocity of either, then that tells me, well, who's going to get there first. So 10 GH over 7, just moving that to the other side, take the square root of that whole thing, and that will give me the velocity of the sphere. Awesome. So let's do the same thing, but this time do it for the hoop. So here I can skip some steps because this piece is going to be the same. So I have mgh equals 1/2 mv squared plus 1/2. Now I need my I, and I is just the total mass times r squared. So my inertia becomes then mr squared, well, times omega squared, which is v squared over r squared. Awesome. So once again, my radius cancels out. I have mass in every term. It goes away, and that gives me just GH equals 1/2 v squared plus, just 1/2 v squared. Oh, a half plus a half, so that's just GH square root of it equals the velocity of the hoop. Rico's not happy. So let's compare that to my V of the sphere. What do we get? Sphere was square root of 10 gravity height over 7. So a couple interesting things there, right? The velocity didn't matter, or didn't depend on the mass. And the radius of either didn't have any kind of impact. It's like they don't matter, which is kind of sad, I suppose. But what does matter then is those coefficients that go with our inertia pieces. So here I can just look at this and I'm like 10 over 7, well, that's a number greater than 1. So the sphere is going to win. It's going to have a higher velocity. Winner, winner, chicken dinner. Winner. And the poor hoop comes in second. But what does that say about energy? Well, in the beginning we wrote, well, let's see, potential energy is going to go into Ke translational plus Ke rotational. Well, if they're both starting at the same height, so the same potential energy, doesn't that mean that these two pieces have to be the same at the end? In fact, it does. So the sum total of these two are the same. But what this means, though, in terms of my translation, is that I have more translational energy, because the V is higher, for the sphere than I do the hoop. Which kind of makes sense, because it takes more energy to rotate the hoop. That's what these moments of inertia mean, right? How hard is it to get something to go? So this is a larger moment of inertia. So more of its energy is going to go into getting it to rotate. So it is going slower. Overall, the two add up to the same, but it's going slower. The sphere is going faster, and it has a much smaller moment of inertia. So less energy had to go into rotating it. So it wins there. It has less energy in rotation and more energy in translation. So one of the things that you can do with this from here is just kind of play around with, well, so how fast are both of them rotating? I'll have you do that on your own. They have the same radius. And if I change my radius, then what does that do to everything? Because didn't we come up with all of these quantities without, or with the radius canceling out? So that matters here, doesn't it? So the larger the radius, if the velocity is the same, then my rotation is slower. Sweet. But again, this still doesn't have mass in it. So mass is going to come into how much energy something actually has. So you can put into your equations here the 1/2 mv squared. So now if I have the same velocity but a different mass, this energy here is going to be larger. Right? So they're not useless quantities. They do matter, but they don't matter. They don't impact how fast it's going. The inertia does. So that's interesting. All right, let's move on to the next topic.